15 billion miles from where you're sitting, a machine built before the internet existed is doing something no scientist can fully explain. It runs on less power than the bulb in your fridge. It was supposed to die in 1981. Instead, it's still awake, out past the edge of everything we call home. And it just sent back data that made physicists use a word they almost never use in public: wrong. Here's the part nobody's covering. In 4 months, this machine crosses a line no human object has ever crossed. A line so far out that a message sent today wouldn't arrive until tomorrow, and the reply wouldn't get back to us until the day after that. Nobody knows exactly what happens once it's out there, alone, on the other side of that line. And here's the part that should really bother you. The thing this machine found at the edge of our solar system doesn't just rewrite a textbook. It touches the shield that keeps deadly radiation away from every living thing on this planet, including you. Stick around. By the end of this, you won't look at the night sky the same way again. I'm Jack Henry. This is the channel for stories science hasn't finished telling. Subscribe. We're just getting started. September 5th, 1977. Cape Canaveral, Florida. A Titan Centaur rocket lifts off the pad and carries a spacecraft the size of a small car into the sky. Its name is Voyager 1, and on paper, its job is almost boring. Fly past Jupiter, fly past Saturn, take some pictures, gather some numbers, and go silent. NASA's own internal planning documents gave it 5 years. Maybe less. The engineers who built it fully expected to be closing out the mission file by 1982. Nobody involved in that launch, not the scientists, not the technicians, not the flight directors, was planning for a sequel. This was supposed to be a postcard from the outer planets, and then nothing. What actually happened is one of the strangest success stories in the history of engineering, and most people have no real sense of how strange it is. Voyager 1 reached Jupiter in March 1979 and sent back the first truly close-up images of that planet's clouds, storms, and moons that human eyes had ever seen. Pictures that rewrote what we thought we knew about the largest planet in our solar system. It reached Saturn in November 1980, threading the gap between the planet and its rings, capturing detail no ground-based telescope could ever hope to match. And then, instead of drifting into retirement the way its mission plan predicted, it kept accelerating. Each planetary flyby worked like a gravitational slingshot, borrowing a tiny sliver of each planet's own orbital momentum and using it to pick up speed, trading a planet's patience for the spacecraft's freedom. By the time the 1980s ended, Voyager 1 had already become the most distant human-made object in history, a title it still holds to this day. And the whole time, that thin radio signal kept coming back to Earth, carrying more data, more images, more proof that the 5-year mission had quietly become something nobody had budgeted for, an open-ended journey to the edge of everything. Then, in 2012, 35 years after it left the launch pad, Voyager 1 did something no spacecraft, no probe, no human-made object had ever done. It left. To understand what that means, you need to picture the solar system differently than you probably do. Forget the flat diagram from your school textbook, the one with neat little rings around the sun. The real solar system is a bubble, a vast, three-dimensional shell inflated by the sun itself. The sun doesn't just throw off heat and light, it constantly exhales a stream of charged particles called the solar wind, blasting outward in every direction at hundreds of miles per second. That wind pushes against the emptiness of space and inflates a colossal protective bubble around everything we call home. Every planet, every moon, every asteroid, every comet, every spacecraft we've ever launched, and every living creature that has ever drawn breath. The outer edge of that bubble, the exact point where the solar wind finally runs out of push and the pressure of interstellar space shoves back from the other side, is called the heliopause. It isn't a metaphor. It isn't a line on a diagram. It is the literal, physical boundary of our solar system. Everything inside that boundary is, in a very real sense, ours. Everything outside it is something else entirely. An ancient, largely unmapped region that no human instrument had ever directly sampled. In 2012, Voyager 1 crossed through that boundary and came out the other side. Sit with that for a second, because it's easy to let a sentence like that slide past you. for the entire history of our species. Every explorer, every empire, every rocket launch, every satellite. Nothing we had ever built had left the solar system. Not technically. Not physically. Voyager 1 became the first. And then it kept transmitting. That means that right now, in 2026, we have a live scientific instrument sitting in true interstellar space. Not orbiting a planet. Not drifting through the asteroid belt. Not hovering near the edge, testing the water. Actually inside the cold, dark, ancient region that exists between star systems. A region no telescope on Earth, no satellite in orbit, no mission to Mars has ever been able to sample directly, because none of them were ever there. And what that instrument has been telling us since it arrived is not what anyone expected. Here's where the story takes its first real turn. For decades before Voyager 1 crossed the heliopause, physicists built detailed mathematical models predicting what interstellar space should look like. These weren't casual guesses. They were rigorous, peer-reviewed models built by some of the most respected minds in physics, and nearly all of them agreed on the broad strokes. Interstellar space should be calm, sparse. A thin, cold, largely uneventful stretch of plasma where particles drift slowly and not much happens. A kind of cosmic waiting room between star systems. Voyager 1 walked into that waiting room and found a storm. Starting in 2017, the plasma wave instrument on board began picking up something nobody had predicted and nobody could immediately explain: a persistent, narrow-band emission. A faint but continuous hum in the fabric of interstellar plasma that, according to every existing model, simply shouldn't exist in the form it was taking. This wasn't a one-time spike that could be written off as sensor noise. It was a sustained signal, tracked year after year across more than 900 million miles of interstellar space. For scale, the distance between the Earth and the Sun is 93 million miles. This hum has now been mapped across a stretch of space roughly 10 times that distance. When researchers published their analysis in the peer-reviewed journal Nature Astronomy, their conclusion was blunt. Interstellar space is not the quiet, uniform void the models described. It has turbulence. It has structure at every scale, from distances measured in meters to distances measured in millions of miles. It is, in a very physical sense, active, restless, in ways that were completely invisible to us until we finally had an instrument sitting inside it. Every model of the universe beyond our solar system had been built from the outside, looking in, built from a planet using telescopes, mathematics, and inference, never direct measurement. The first instrument humanity ever placed on the inside just told those models they were missing something fundamental about the structure of the universe immediately outside our front door. And here's why this stops being an abstract physics story and becomes a personal one. The same bubble that separates our solar system from that turbulent outer region is the same bubble that shields every living thing on Earth. The heliopause isn't just a line on a scientific diagram. It functions as a shield, deflecting the most dangerous high-energy cosmic radiation, the kind that streams in from distant supernova remnants before it can reach the inner solar system at full strength. If that shield behaves differently than our models assumed, if it's more porous, more variable, or more reactive to outside pressure than we thought, the implications for biology on Earth over long enough timescales are not small. We don't yet know exactly what a more turbulent, more energetic interstellar environment means for the long-term stability of that shield. But the fact that credible scientists are now asking that question at all marks a genuine shift in how we understand our own exposure as a species, sitting on a small planet inside a bubble we're only now beginning to understand from the inside. Before we get to the discovery that reads less like physics and more like science fiction, you need to understand what almost ended this entire mission for good, because it happened recently, and it happened quietly. November 2023. Voyager 1 kept transmitting on schedule exactly as it had for 46 years. But something was wrong with what it was sending. The signal was gibberish, corrupted code, scrambled data that the engineers at NASA's Jet Propulsion Laboratory, people who had spent entire careers learning to read this spacecraft's every heartbeat, simply could not decode. The spacecraft was alive. The signal was arriving on schedule. But whatever Voyager 1 was trying to say had become unreadable, and for a team that had successfully operated this mission since the Carter administration, that had never happened before. The cause, once they finally traced it, was both simple and unsettling. A single memory chip inside the spacecraft's flight data subsystem, a component roughly the size of a fingernail, had physically degraded after nearly 5 decades of continuous exposure to cosmic radiation, the harshest environment any human-made object has ever operated in for this long. No alarm had gone off. No warning had been logged. The chip had simply quietly failed, corrupting the section of code responsible for formatting and transmitting scientific data back to Earth. In an ordinary engineering failure, you fix a broken part by walking over and replacing it. That option didn't exist here. The failed component was roughly 15 billion miles away, unreachable by any spacecraft humanity has ever built, with no repair mission conceivable on any timeline that would matter. The only tools available were radio waves, and even traveling at the speed of light, those waves took 22 hours to reach Voyager 1, another 22 hours for any response to travel back. Every single diagnostic step required a minimum 44-hour round trip just to complete one exchange of information. Picture what that actually looked like from inside the control room at JPL. You study a fragment of data. You form a theory about what might be wrong. You write a careful set of instructions to test that theory. You transmit it, and then you wait. Not minutes, not hours. A full day and a half before you know whether your test even reached the spacecraft, let alone whether it worked. You receive the response. You analyze it. It's slightly different from what you expected. You revise your theory, write new instructions, transmit again, and wait another 44 hours. Now repeat that cycle for months, with the full knowledge that a single incorrect instruction sent once across 15 billion miles of empty space could permanently end the mission with zero chance of recovery. No backup ship, no second try. The team at JPL worked through that pressure for months, methodically, patiently, under a kind of engineering stress that most missions never come close to producing. And they succeeded. They determined the corrupted code itself couldn't be repaired in place, but it could be relocated. They split the affected software into smaller sections, rewrote each piece individually so it would function correctly from a new location in the spacecraft's limited memory, and carefully reconnected the pieces so the whole system worked as one again. It was, in effect, brain surgery, performed remotely through a 44-hour communication delay on a patient built in the 1970s, sitting 15 billion miles from the nearest surgeon. By mid-2024, Voyager 1 was back online, transmitting clean, complete, readable scientific data once again. And the very first thing it resumed sending home was more evidence of that same unexplained plasma turbulence out in interstellar space. More proof of the structure the old models never predicted. A spacecraft that should have gone silent in 1981 had just survived a near-fatal failure 46 years later in 2023, and came back with more to tell us. None of that. Not the discovery, not the near-death, not the recovery. Prepared anyone for what Voyager 1 had actually found the moment it crossed the heliopause back in 2012. This is the part of the story where the scientific papers stop reading like physics and start reading like something else entirely. For decades, models of the heliopause predicted a gentle transition, the solar wind gradually thinning out on the inside, the interstellar medium gradually becoming detectable on the outside, a slow, smooth blend at the seams, the way a river eases quietly into the sea, no sharp line, no drama. That is not what Voyager 1 found. At the heliopause, particles weren't drifting apart calmly. They were slamming into each other at speeds approaching a meaningful fraction of the speed of light, generating temperatures near 30,000 degrees Celsius, hotter than the surface of most stars. Not inside a sun, but at the outer edge of our own solar system, in a region models had described as relatively cold and sparse. Some researchers studying this region have described it, without exaggeration, as a wall of fire, a genuine physical concentration of ultra-energetic charged particles sitting right at the border of everything we call home. Then came the second surprise, and this one struck even deeper at the foundations of the models. For decades, One of the core predictions about the heliopause was that the magnetic environment would change sharply the moment you crossed it, inside the bubble, the sun's magnetic field. Outside, the entirely separate magnetic field of the galaxy. Two distinct systems, cleanly divided at the boundary, the way two countries might be divided by a fence. Voyager 1 found something completely different. The magnetic fields on both sides of the heliopause weren't cleanly separated at all. They were, in ways existing theory had not predicted, connected. The sun's magnetic field lines, stretched outward by the solar wind and compressed at the boundary, were interacting directly with the galaxy's magnetic field outside through a process called magnetic reconnection. The same basic physics that powers solar flares, where field lines from different sources rearrange themselves and release bursts of energy in the process. Translation: our solar system isn't magnetically sealed off from the rest of the galaxy. It's linked to it. Energy is being exchanged, right now, at the boundary between everything we know and everything we haven't yet explored, in a way that every model built before Voyager 1 crossed that line simply failed to account for. This isn't a footnote buried in a technical appendix. If the relationship between our solar system and the wider galaxy is more dynamic, more connected, and more energetic than we assumed, then our understanding of how the heliosphere protects Earth, over not just years, but geological timescales, needs to be reconsidered from the ground up. Now let's talk about right now, 2026, because this story isn't finished. It may, in fact, be entering its final chapter, and the timeline is tighter than most people realize. Voyager 1's power comes from 3 radioisotope thermoelectric generators, essentially sealed containers of plutonium-238 that produce heat as the plutonium slowly, steadily decays. That heat gets converted into electricity. At launch in 1977, those generators produced roughly 470 watts. Today, nearly 49 years later, that number has fallen to somewhere around 250 watts. The decline is steady and unstoppable, about 4 watts lost every single year, with no way to slow it down. Of the 10 scientific instrument packages Voyager 1 launched with, 7 have already been permanently switched off. Not because they broke, but because there simply wasn't enough power left to keep everything running at once. Earlier this year, the team made one of the hardest calls yet. The low-energy charged particle instrument, which had been gathering data almost without interruption since 1977, was shut down. Not because it failed, because the power budget couldn't support it anymore. These are not easy decisions. Every instrument the team switches off represents a category of questions that may never get answered again, and there is no way to flip an instrument back on once you've decided you turned it off too soon. The engineers and scientists who run this mission worked out years ago, carefully and deliberately, which instruments to sacrifice and in what order, trying to squeeze the maximum possible scientific return out of a dwindling, irreplaceable power supply. But here's the twist that isn't making many headlines. The team hasn't given up on buying more time. NASA engineers have reportedly been testing an experimental power redistribution procedure, an attempt to restructure how electricity flows across Voyager 1's remaining systems in order to squeeze out additional capacity from components currently running below peak efficiency. It's a technically delicate idea, and a risky one, because even small changes to the power architecture of a nearly 50-year-old spacecraft, one with no manual override, no backup crew, no way to intervene if something goes wrong, could produce unpredictable results. So the team has been testing the concept first on Voyager 2, which carries a bit more power margin and sits somewhat closer to Earth, making a failure there less catastrophic to the overall mission. If those tests confirm the approach is safe, the same procedure could eventually be attempted on Voyager 1. And if it works, there's a real possibility that some of the instruments already shut down, including the ones silenced earlier this year, could be switched back on. Nobody on the team is making promises. But with this particular spacecraft, betting against it has never aged well. And then there's the date already fixed on the calendar, the one arriving no matter what. On November 18th, 2026, at 2:16 a.m. Pacific Time, Voyager 1 will cross a threshold no human-made object has ever reached. It will be exactly 1 light day from Earth, a distance of roughly 16.1 billion miles, or about 173 astronomical units. At that distance, a radio signal traveling at the fastest speed anything in the universe can travel takes a full 24 hours just to arrive. Send a command on a Monday, and you won't know if it landed until Tuesday. You won't hear back until Wednesday. 2 full days just to complete a single exchange. No object built by human hands has ever been that far away, not once in the entire span of civilization. And Voyager 1 will cross that threshold while it is still alive, still transmitting, still doing science, and then it will simply keep going. Every hour, it puts another 38,000 miles between itself and home. The communication delay keeps stretching. The power supply keeps shrinking. And at some point in the early 2030s, current projections suggest the last usable signal will arrive, and after that, there will be nothing more to receive. Even when that final signal comes and goes, Voyager 1 itself doesn't stop. There's nothing out in interstellar space to stop it. No friction to slow it, no atmosphere to burn it up, no gravity strong enough to meaningfully pull it off course. It will simply keep sailing in a straight line, silently, at roughly 38,000 miles per hour, into a darkness that has no meaningful end on any timescale a human mind can hold on to. But it isn't traveling empty. Bolted to its frame is the Voyager Golden Record, a gold-plated copper disc carrying greetings recorded in 55 human languages, the sound of rain falling on a forest, the roll of ocean waves, the sound of human laughter, 90 minutes of music drawn from cultures spanning the length of recorded human history, diagrams explaining the basic principles of our mathematics and physics, and a map built from the positions of pulsars, designed so that whoever eventually finds it can calculate exactly where, in this galaxy, our small planet sits. Carl Sagan, who helped design the record, described it as a message in a bottle cast into the cosmic ocean. That description has never felt more accurate. Whoever, or whatever, eventually encounters it, whether that's another civilization a million years from now, or some form of intelligence we currently have no framework to imagine, that record will tell them something simple and true, that a species existed here, that they were curious, that they reached outward, and that they built a machine out of metal, electricity, and careful mathematics, and sent it beyond everything they had ever known, carrying the recorded sound of their own laughter. The record will still be traveling long after the sun swells into a red giant and swallows the orbit of the Earth. It will still be moving after every human city, every archive, every name we've ever carved into stone has been worn away by geology and time. It is, quite plausibly, the single most permanent object our species has ever created, and it's riding on a spacecraft that currently runs on less electricity than the light above your kitchen sink. Let's come back to the science, because there's one more piece of this story that deserves to sit at its center. That persistent plasma hum Voyager 1 has been detecting since 2017 isn't just a strange anomaly. According to the researchers analyzing it, it represents the first continuous, real-time measurement of interstellar plasma density humanity has ever obtained. Before this emission was detected, scientists could only capture isolated snapshots of plasma density out there. Measurements triggered by rare events, like the shock waves produced when a massive solar eruption finally traveled all the way out to the heliopause and rippled into the interstellar medium beyond it. Those snapshots were valuable, but scattered, like trying to understand a continent's climate from a single thermometer reading checked once a year in one city. What the persistent emission gives us instead is something closer to a running feed, a continuous portrait of interstellar plasma building day after day, year after year, as the spacecraft physically moves through it. And what that portrait shows is that interstellar space is not a static, uniform backdrop. It has texture. It has something close to weather. It has structures built from charged particles and magnetic fields that stretch for millions of miles and interact with the outer edge of our solar system in ways no Earth-based model ever anticipated. The space between stars is not empty. It's active. It has a physical personality that we are only now, for the first time in the history of our species, beginning to actually read. But there's a genuine, unresolved question sitting at the center of this discovery, and researchers haven't been able to settle it yet. The persistent emission has two possible explanations. The first is that it comes from thermally excited plasma oscillations, the natural vibration of plasma particles interacting with their environment. That would be a real discovery, but one that fits comfortably inside existing physical theory. The second possibility is something called quasi-thermal noise, a distinct physical mechanism that would carry information about plasma, density, and temperature in a meaningfully different way, and one that would require our existing models of the interstellar medium to be substantially rewritten. Telling these two explanations apart requires either more data from Voyager 1, which produces less of it every single year as more instruments go dark, or an entirely new mission, purpose-built to study interstellar space with instruments designed for exactly this kind of measurement. That mission doesn't exist yet. It isn't funded. And even under the most optimistic timeline, if such a mission were approved and built starting today, it wouldn't reach the heliopause for at least another 25 years. Which means that when Voyager 1 finally goes silent, whenever that day arrives, the question it raised falls silent along with it. The only real-time window our civilization has ever had into interstellar space will close, and it will very likely stay closed for a generation, maybe longer. Here's the part I want you to sit with, because it's easy to get lost in the physics and forget the simple fact sitting underneath all of it. Right now, in 2026, the only live scientific instrument humanity has ever placed in interstellar space is 48 years old. It was designed using technology that predates personal computers, predates the internet, predates almost everything we consider modern engineering. It runs on less electricity than the bulb above your kitchen stove. And it is, right now, quietly rewriting our understanding of the universe and our place inside it. We've built things far larger, far more powerful, far more expensive, involving technology the spacecraft's original engineers couldn't have dreamed of. And none of those things have told us what Voyager 1 is telling us, because none of them had the one thing this machine has always had, the audacity to keep going long enough to actually get there. There are questions about the universe that can only be answered from inside it, not from a telescope on the ground, not from a satellite in orbit, not from a mission to Mars or the asteroid belt. Only from a machine that physically crossed the heliopause and kept transmitting from the other side. We have exactly one such machine. It is old. It is fading. It runs on 4 watts of power. And as long as it's still talking, we owe it the simple act of listening. Because when it finally goes quiet, the answers to some of the most important questions we've ever asked about our place in the universe go quiet with it, at least for a generation. The signal is still coming, stretched across 15 billion miles, delayed by 22 hours of travel time, carrying proof of a universe stranger, more turbulent and more connected than any model built from the safety of Earth ever managed to predict. One machine, 4 watts, one chance to listen while it lasts. If this is the kind of story you come here for, subscribe and turn on notifications, because we're going deeper into the edges of what science actually knows next time. Drop a comment with what surprised you most in this video. And if you know someone who'd want to hear this, send it their way. This story deserves more attention than the silence it's been getting. Thanks for watching.